So we continue with Roberto Unger and Lee Smolin, One Single Universe. And I will specifically clear out here that we're speaking about the part written by Roberto Unger. And although it doesn't contain any difficult jargon, it is one of the most difficult texts I ever encountered. And the only comfort is to reading the critique of the texts or the books and see that the critique doesn't cover the understanding, or the one making the critiques haven't understood. And I think it's verging on the absurd to say that the argument against many worlds is just about many worlds, and the view taken by Hugh Everett and Max Tegmark and others, it is much, much more. There's a lot more to it. But in the beginning we can be happy with it actually takes away all risk of ever hearing anything about new worlds or more worlds, or not even a second world would be possible here. Well, I just cut to the chase and go into it. Wherever, as in most of the observed universe, there exists a differentiated structure, a clear distinction between states of affairs and laws of nature, and tight constraints on what can happen next, the change of change will be rare. It will take the form of the appearance of emergent phenomena with new properties, displaying new regularities, or governed by new laws. Such is the case with the phenomena studied by the earth and life sciences. And then again with those realities that we address when we try, through the study of mind, society and history, to understand ourselves. Complexity may expand the range of adjacent possible, of the theirs that nature can reach from any given here. In so doing, it creates a basis for emergent phenomena, exhibiting novel regularities. Suppose nature can also exist in another form. The second state evoked in my discussion on the second cosmological fallacy, in which there is no differentiated structure and no clear contrast between laws and phenomena, in which many degrees of freedom are excited, and in which there persists ample transformative opportunity. In such a state, the restraint on the change of change will be weakened. Degrees of freedom, the adjacent possible, the emergent phenomena and properties will no longer be concepts that can be clearly distinguished when applied to such a presentation of nature. We are accustomed by the dominant tradition of physics, established as the supreme model of successful science, to regard historical explanation as ancillarily to structural explanation. On the view that we here defend, this hierarchy must be reversed. Structure results from history. Historical explanation is thus more fundamental than structural explanation. Cosmology affirms its ambition to be the most comprehensive natural science when it understands itself as a historical science first, and as a structural science only second. The primacy of historical over structural explanation should give no offense to science, so long as we qualify the demand for causal explanation of everything in two ways. Neither of which would be acceptable to those who espouse the metaphysical rationalism of Leibniz's principle of sufficient reason. The first qualification is that we allow a historical explanation to count as a causal account in cosmology and physics as in other branches of science, indeed as the most characteristic form of causal explanation when the subject matter of science becomes the whole universe. Under a historical view, a state of affairs is the way it is because of the influence of an earlier state of affairs, not because it conforms to timeless and invariant regularities. we shall not always be able to account for the influence of the earlier on the later by invoking such regularities. The second qualification is that we be willing to pay the price of a practice of historical explanation that is not subordinate to structural explanation. The price has in turn two parts. The first part is that there is no absolute beginning. Time, we argue in this book, is not emergent. At any given time, at any given moment in the history of science, our ability to draw account time has no beginning. Thus, historical explanation is by its nature incomplete. The second part of the price is that change is how change occurs, as described by a historical science, has an ineradicable matter of factness or facticity. We can increase the extent to which we are able to make sense of the transformation of transformation. At the end of the day, however, nature will always be found to have an irreducible, factitious element. It is what it is. If it were not what it is, but rather the consequence of some mode of rational necessity, history would once again be subordinate to structure. Here history reminds me of the Heideggerian concept of Geschichte, in contrast to history, which is subordinate to structure. We can attenuate such just soness. We cannot abolish it. Examples of how we can attenuate it are the proposals that we make later in this book for the resolution of the dilemma of the meta-laws in cosmology, conceived as a historical science. We have reason to resist accepting either that change of laws of nature is governed by higher order laws, or that it is not. These propositions require us to believe that the workings of nature are not necessary, even though they are causally determined. There is no univocal, unambiguous notion of necessity in science. Necessity designates the limit of the least mutable realities that are represented in a given set of ideas. What is necessary is whatever, according to that way of thinking, could at least be other than it is. In the tradition of physics that began with Galileo and Newton, the content of this limiting ideal of necessity is given by the convergence of three commitments. The first commitment is to what we call the Newtonian paradigm, the extrapolation to the whole universe of an explanatory strategy. Distinguished by the contrast between initial conditions and timeless laws applying within a configuration space demarcated by stipulated initial conditions. This procedure is legitimate only when applied to parts of the universe. To repudiate its cosmological application was the aim of my argument against the first cosmological fallacy. The second commitment is to the premise that the characteristic form of the observed cool-down universe, with its stable, differentiated structure, its apparent contrast between laws and phenomena, and its severe constraint on degrees of freedom, on the range of adjacent possible. And on the facility for the appearance of emergent phenomena and properties, that is to say, of the new, is the only form of nature. To reject this temporal generalization of the form that nature takes in the cool-down universe was the purpose of my criticism of the second cosmological fallacy. The third commitment is to the sovereignty of mathematics over physics. On the view presupposed by that commitment, what is physically realized is what can be mathematically represented and justified. Mathematics stand to physics as both oracle and prophet, divining the ultimate nature of reality. Given the non-temporal and ahistorical character of the relations among mathematical propositions, this commitment is intimately related to the assumption of the immutability of the laws of nature and to the invariance of its symmetries. Expressed as mathematical equations. One form of this ambition is to conceive the universe as isomorphic to a mathematical construction, or even as a mathematical structure. Another form is to infer the laws and symmetries of nature from the most consistent and comprehensive mathematical ideas. To contest the third commitment is the goal of my discussion of mathematics in chapter 6. Neither any law or symmetry of nature, however fundamental it may appear to be, nor any working of causality, in the absence of such laws and symmetries, is necessary if by necessity we mean an idea of necessary realities and relations that is defined by the coexistence of these three commitments. It does not follow, however, that the meaning of the thesis of causality without laws is to affirm the radical contingency of the way in which nature at any given time works. Radical contingency is a metaphysical, not a scientific idea. Its function is to express a disappointment that we cannot infer the way things are from the imperatives of reason. That is, in the spirit of Leibniz's principle of sufficient reason. Its invocation betrays bad faith or confusion, as surreptitious genuflection to rationalist metaphysics by those who pride themselves of having cast off its shackles. It is an homage that has often had an ulterior religious, moral, or political motive. The way things are is, for science, just what they are. The subordination of structure to history ensures the defeat of the rationalizing metaphysical project that the dominant tradition in physics has patiently served. It has served this project in the conviction that in so doing it would be able to wed mathematics and serve itself. As a dowry, it received from mathematics a poison gift, a pharmakon, the means with which to explain temporal events by timeless laws. Structure results from history. The combination of fundamental historical explanation with derivative structural explanation is the basis of science. It falls to science to make sense of how and why the workings of nature are what they are. To guard against illusion, it must do so, however, without taking the why part of this endeavor as an invitation to infer natural reality from rational necessity. The universe is more neutrally described as factitious than as radically contingent. Its most important attribute is that it is what it is rather than something else. It is what it is because it was what it was. Causality and historicity are embedded, not two separable items like a scissor and needle. Chapter 2. Thank you again for your patience. It's getting smoother. The context and consequences of the argument. The argument and recent physics and cosmology. The historical context of the argument helps clarify its intentions. Consider 4 such contexts. The physics and cosmology of the last few decades. The physics of the first half of the 20th century. The rise of the life sciences and their relation to physics, and the study of human history and society. To place the argument in these multiple contexts is to understand how much is at stake in these disputes. It is also to undermine the fake authority that clings to widespread ideas about the plurality of worlds, the restricted reality of time, and the power of mathematics to serve as a privileged window of reality. In its relentless quest for a definitive unification, a view that would bring gravity under the same theories that account for the electromagnetic, the strong and the weak forces. Much of the contemporary physics and cosmology has despaired of explanations that meet the traditional and exacting standards of either deterministic or probabilistic causality. It has settled for explanations that admit a vast array of states of affairs, of which the observed states of affairs represent no more than a particular variations. Rather than acknowledging such underdetermination as limit or failure of insight, it has tried to turn a detriment into benefit by describing the former as the letter. In particle physics, the chief vehicle for this operation has been string theory. The results have yet to meet the explanatory standards of classical physics. Only a few of the resulting equations or of the specifications of the parameters describe states of affairs that we find in the observed universe. The large preponderance of the equations or their admissible parameters refers to circumstances that we have never found and may never in principle find. The temptation is strong to convert the explanatory embarrassment into explanatory triumph by fiat. Such a conversion of failure into success relies on the thesis that the unobserved states of affairs allowed by equations exist somewhere else. In cosmology, the move has been from the conception of an inflating universe, even an eternally inflating universe, to the idea of a multitude of unobservable universes, a multiverse. The reciprocal adjustment that I earlier mentioned applies here with a vengeance. The actual observed world, the only one we do or ever could observe, lends some of its reality to the many other unobserved and unobservable worlds. It becomes less real so that they can become more real. The distinctions between the mathematically conceivable and the physically possible, and then between the physically possible and the physically actual, are attenuated or even effaced. In both particle physics and cosmology, the explanatory failures of the doctrine of multiple universes find partial relief in to the so-called anthropic principle. In its strong version, this principle seeks to explain the observed states of affairs backwards as the uniquely selected variations on the possible or actual states of affairs from which we humans who now observe and theorize could emerge. How gallantly. One instance of special pleading is pressed into the service of another. The outcome is a watering down of the rules and standards by which the practice of natural science has been conducted over the last few centuries. On one side, it's a dilution of the task of causal explanation to explain why things are what they are, not just to show how they are possible or susceptible to mathematical representation, among many other things that no one has seen or ever even could see. Instead of trying to show how the possible become actual, such a way of thinking rests content with the discovery that the actual can be brought under the aegis of ideas that are also compatible with the vast array of states of nature that no one has ever or could ever observe. Together with this inversion of the standard task of explanation goes further movement in a direction that much of physics has been taken for a longer time. The substitution of structural analysis for causal explanation. Views of how things are put together instead of ideas about why they change into other things. On the other side, weakening the standards of natural science takes the form of a distancing from the discipline of empirical verification or falsification. It is one thing to develop a theoretical apparatus that becomes verifiable or falsifiable only at the periphery of its implications. The core ideas and presuppositions are subject to empirical challenge, albeit indirectly through the testing of such implications. It is another thing to propose theories lacking in the power so to be challenged through critical experiments or observations, even at such a periphery. The twofold dilution of determination and of empiricism, made more visible by the appeal to the strong anthropic principle, sounds as the 13th chime of a clock, which not only disturbs us, but also makes us wonder about the previous 12 chimes. The tendencies in recent physics and cosmology that have produced this outcome demonstrate the consequences of relying on assumptions that it is the purpose of our argument to oppose. That our universe is best understood as simply one of many. That time is less real than it seems to be, that in any event, it does not threaten the permanence either of the basic structures of nature or its fundamental laws, which supposedly govern the crowd of universes. All but ours inaccessible to observation, and that mathematics, as the language in which such timeless laws about the multitude of worlds are written, offers privileged insight into ultimate reality. The scientific practices and theories that have preceded these ones proceeded on these assumptions, break with the requirements of explanatory power and vulnerability to empirical test. That together with a theoretical imagination have enabled natural science to progress on its revolutionary course over the last 300 years. Any assumptions that threaten to derail science from this course by weakening the disciplines that chasten and guide it deserve to be reconsidered. The argument and the physics of the first half of the 20th century The physics of the first half of the 20th century undermined the idea characteristic of Newtonian mechanics, that we can draw a clear distinction between the physical events of the world and their setting in space and time. In the two-step movement of special relativity and general relativity, Einstein destroyed the basis for this distinction. Space-time became part of the unfolding drama rather than just a piece of the unchanging background. In this respect, the new physics reinstated what had always been a tradition, although a suppressed or recessive one. Within the old physics, the relational view most famously associated with Leibniz. According to this view, each event is the sum total of its relations to other events. Space-time forms part of that relational grid. It is not its changeless seat. The argument of this book bears on this momentous shift in the following way. In tearing down the contrast between the events and the background in space and time, the new physics nevertheless reaffirmed two other distinctions of many-sided importance, which it should now be our aim to overturn. The first was the difference between the phenomenal world and an invariant background, not of space and time, but of universal laws and symmetries, and elementary constituents of nature. In the methodological disputes provoked by the rise of quantum mechanics, the focus fell on the respective claims of deterministic and statistical explanation. All parties to the dispute continued to accept the idea of unchanging and generally applicable laws. The second was the distinction between initial conditions and law-like workings of nature in a configuration space bounded by such conditions. A straightforward way to state the core thesis of our argument is that these two distinctions, reaffirmed by the revolutionaries of the early 20th century, now deserves to be cast aside. Consider the relation between the two contrasts that we reject. The difference, so central to established physics, between stipulated and initial conditions, stipulated initial conditions, and the law-like workings of nature within a certain region of reality, a configuration space, breaks down when we try to apply this distinction to the universe as a whole. The boundaries of configuration space then become those of the universe. There is no place outside this one real world from which to deliver the specified initial conditions. Nothing remains other than the universe and its history. We can no longer say, as we do when dealing with a segment of the universe or a part of reality, that what is given as a brute fact from the standpoint of the laws that account for the workings of local phenomena may become a subject of explanation by other laws. Such other laws might apply when we redraw the boundaries of the configuration space. When, however, we deal with the whole universe, we cannot redraw boundaries in this way. We have reached the top. We have nowhere else to go. And this is an incredible, decisive blow to the idea of multiple universe, or multiverses as they're often called now. And it's important to remember and helpful to understand this was so to say, implicit. Multiverse ideas was implicit from the very beginning. It was just one way we had to go because of how we arranged things. That the world was ruled by determinate laws, unchanging, made it impossible to avoid multiple worlds. Now when string theory has failed to give the answers on the basis of immutable laws. So what needs to be given up is the idea of unchanging laws. Another way of looking at it is to say that the universe is singular. There's nothing beyond what we can observe or be in. A very, very important message to the world, I would say. Might be the most important one to come up in the 20th century. Very important. I end there. It's time enough. Thanks once more for your patience. It is clearing up. It is becoming more and more digestible stuff to get it, but once it's there, it progresses somehow. This is my feeling right now. Have a very pleasant afternoon and see you soon. Bye bye.